Good afternoon to all. Am I audible? I'll start the class within 2 minutes. my voice is not clear, if there is any disturbance, inform. My voice is not clear, and if there is any disturbance, inform. Okay, I'm going to start the class. If my voice is not syncing with the screen, you just inform me. I think there will not be any disturbance. Everything will go okay. If there is an issue, just mention in the chat box. Okay, I'm going to start the class now. So single phase transformers. So you can see a transformer here. So this is a transformer. So purpose of the transformer is to transfer the AC power from one circuit to another circuit at constant frequency. So we can transfer the power from one circuit to another circuit using this transformer. So whenever we want to vary the voltage levels, okay, so if you want to change the voltage level of one circuit to the another circuit, so simply using the transformer we can either increase the voltage level or we can decrease the voltage level with the help of this transformer. So transformer works on the principle of Faraday's law of electromagnetic induction. It states that the magnitude of voltage will be always directly proportional to the rate of change of flux. Means E is equal to, I will expand the screen. So according to Faraday's law of electromagnetic induction, the voltage, sorry, this my cursor, I have an issue with my cursor. So the voltage, you can write voltage as V or E. So E will be equal to, okay, okay, I will write proportional, not equal, proportional to D, that is d phi by dt. I didn't write it properly. Okay, E is equal to, E is directly proportional to d phi by dt. Okay, in the generator principle, isn't it generator principle? The induced voltage E will be directly proportional to the rate of change of flux linking with the conductor. Induced voltage will be directly proportional to the rate of change of flux linking with the conductor. So E is proportional to, my cursor is not listening to me. So E is directly proportional to d phi by dt. Okay, E is directly proportional to dφ. That is Faraday's law of electromagnetic induction. Okay, so purpose of transformer is what? To transfer the power from one circuit to another circuit and to change the voltage levels. Either we can step up the voltage level, means low voltage can be converted into high voltage, or high voltage can be converted into low voltage. Okay, so if you see, this is the schematic diagram of your single phase transformer. So you can see here there is a core. This is known as core. This square shaped structure what you see here is the core. So inside this portion is hollow. It is simply air will be there in this section. Okay, so it has this section, you know, this section, right? So this section is one limb, this section is another limb. So two limbs are there. The upper horizontal sections, these two are known as yoke. So this core has two limbs. Vertical portions are known as limbs and horizontal portions are known as yokes. So upper yoke and lower yoke and vertical limbs. So to whichever limb we can take a wire and we can wound it around both the limbs. Okay, so you can see green color wire wounding around this limb. This is a conductor. This green color thin line like water coil that we can see is the conductor. This red color coil that we can see is also the conductor. So this is the conductor coil. This is also the conductor coil, the green color and red color. Okay, so to whichever coil you connect the AC supply, you can see supply here, AC supply. So to whichever coil you connect the supply, that coil you call it as primary winding. Okay, so the other coil you call it as secondary winding, to which we will connect the load. Okay, the coil to which you connect the load, that is known as secondary winding. Okay, so this device transformer, it is this transformer you call it as a static device. Why? Because it won't have any moving parts. Transformer is known as a stationary device, or you can call it as a stationary circuit. Okay, so when supply is given, so here, where is my cursor? Yeah. So is my voice linking with the screen? Anyone, can you mention in the chat box? Is there any disturbance, or am I audible, or is my voice linking with the screen? If it is not linking with the screen, means it is not matching with the screen, inform. Those inform your friends. Some of your friends told me that they are not receiving any notification. That's why they are unable to attend the class. You just inform your friends to join the class. Is my voice audible? Is there any disturbance? Let me check myself. Am I audible? Is my screen linking with the screen matching with my voice? Can anyone inform me? If there is any disturbance, if my voice is not matching with the screen, inform. Okay, I proceed. So, when supply is given, when AC supply is given to the circuit, When AC supply is given to the circuit, current will flow into the circuit. Because of the flow of current, let us assume supply voltage Vs volts is given to the circuit. So current of I1 amperes flows through this coil. When current flows through this coil, what will happen is, we already know, when current flows through when current is flowing through this coil, so since this coil is wounded across the, what is say, across the ferromagnetic material, so this core is made up of ferromagnetic material. Okay, this core is made up of ferromagnetic material, so which can be easily magnetized. Okay, which can be easily magnetized. Therefore, what will happen is, when current flows through this coil, this limb gets magnetized. Okay, this limb gets magnetized. When this limb gets magnetized, flux phi is induced in this limb, and this flux, you can see here dotted line, this flux will travel through this core. Okay, and it will travel through the other limb. So when this flux travels through the other limb, so when we know, when either magnetic field moves or when the coil moves, EMF is induced. So when this flux is traveling through this limb, it cuts this coil. Therefore, what will happen? Voltage is induced, some E2 voltage. Similarly, here also, when current flows through this coil and when flux is induced, here also voltage is induced. So E1 voltage is induced in the primary winding, E2 voltage is induced in the secondary winding, and when you connect the load, what will happen is, current of I2 amperes will flow through this load. Current of I2 amperes will flow through this load. So this core, okay, this core, magnetic core, we will call it as magnetic core. This magnetic core, it provides a magnetic path for the flux to get linked with the secondary winding. The purpose of the core is what? It provides the magnetic path for the flux to get linked with the secondary winding. Okay. So whatever flux, here I am showing you only one flux line. You can see here in this diagram many flux lines. All these green dotted lines are flux lines. All these green dotted lines, what you can see are the magnetic flux lines. Yeah, all these are magnetic flux lines. Okay, so I'm looking for some diagram. Yeah, so whatever flux that is induced in the core, so that whole flux may not travel from this limb to the other limb. Some of the flux may be wasted. Okay, some of the flux may travel into the air. That flux is known as leakage flux. That flux is known as leakage flux. Okay, so whatever amount of flux that travels through the core, that flux is known as main flux. So while traveling from this limb to this limb, some of the flux may be wasted or it may leak into the air. Okay, so whatever flux that is able to travel from this limb to the other limb, that flux is known as magnetic flux. So after reaching the second limb, it will return back to wherever it has been initiated. So this flux forms a closed path. Okay, so you can call this flux as the magnetic circuit. Okay, so this flux itself forms a magnetic circuit. Okay, so for the flux lines to flow, okay, for the flux lines to travel, the core should provide a low reluctance path. So what is reluctance? Reluctance is the property of the material which opposes the magnetic flux. Okay, so we know resistance. Resistance is the property of the material which opposes the flow of current. Similarly, flux opposes the flow of flux. Okay, as resistance opposes the current, reluctance opposes the flux. Sorry. Okay, reluctance is the property of the material which opposes the flux. So the material in which the magnetic flux lines are traveling, that material should have low reluctance path. Okay. So this main flux, this main flux, you can even call it as a useful flux. Okay. So, and this leakage flux, you know, whatever leakage flux is there, it will never gets linked with the secondary winding. Only the useful flux or main flux gets linked with the secondary winding. So what is happening here? EMF is induced in the primary winding as well as this is the symbolic representation of your transformer. So this is our primary winding. Okay. So this is primary winding. This is secondary winding. In the winding, voltage is induced E1. In the secondary winding, voltage is induced E2. So this is I1 current. Here I have written I2. Okay, this is not I2. This is I1. Not I2, it is I1. So supply voltage that we are giving here is V1. Okay. So whatever voltage that is induced in the secondary, okay, whatever voltage that is induced in the secondary winding, which is our secondary winding, this is our secondary winding. So whatever voltage that is induced in the secondary winding, this winding, that voltage we will call it as mutually induced EMF. Okay. And the frequency of this in mutually induced EMF will be same as the supply frequency. Okay. So here we didn't write I2 current. Why? Because we didn't connect any load. If we connect any load, we can mention I2 current since the load terminals are open. Therefore, we didn't mention any I2 current. Okay. Now here there is no electrical connection between this primary winding and the secondary winding. This is the primary coil. This is our secondary coil. We didn't mention the core here. So if you want to mention the core, we can mention that. I will take a, if, in order to mention the core, what you have to do is you have to, sorry, I have an issue with my cursor. So this is I1. So I will just erase it. I might have removed it. I didn't edit this image. So I will better, okay. So here you can see I1 current, supply voltage V1, E1 current, I'm sorry, E1 voltage, sorry, and E2 voltage. Since we have connected the load, I2 current. Okay. So symbolic representation of transformer is simply a coil. Okay. Just this is it. This is primary coil, secondary coil, two parallel lines. Okay, so this is a symbolic representation of a transformer. So I might have drawn here. I was unable to, I will try my best. I am unable to draw the lines, two parallel lines here, but I will try. So, so this is what happens if I am drawing anything. So this is not there. Okay, these two parallel lines. These are the two parallel lines. So this is the symbolic representation of the transformer with two parallel lines. Okay, so uh, if V2 is greater than V1, means V2 means E2. Okay. So if this is E2 or V2, your wish, we can give any notation. Okay, E1 and E2. So if the induced voltage in the secondary terminals is greater than the induced voltage on the primary, then we call the transformer as step-up transformer. If the voltage at the secondary terminals EV2 or E2 is less than the primary voltage, then we will call it as step-down transformer. Okay, step-up transformer means the voltage at the secondary terminals will be higher than the. Okay, someone wrote in Hindi in the comment box. He wants something. Let me check. Reply then. Okay then. So let us proceed. So step up transformer and step down transformer. So notations, sometimes we write E or sometimes we write V. V or E, irrespective of V or E, we can, what are maybe the notation? So both are voltages. So if suppose the induced voltage around the secondary terminal is higher than the induced voltage on the primary side, then that is step up transformer. And if the induced voltage on the secondary is less than the primary side voltage, then that is a step down transformer. So usually transformers are used to step up the voltage levels or the step down the voltage levels. Okay. So here, since we can see here, okay, yeah, you can see here there is no electrical connection between primary and the secondary. Therefore, we can say purely due to mutual inductance, okay, purely due to mutual inductance, electric power is transferred from the primary winding to the secondary winding, and the induced voltage E1 value, okay, the induced voltage E1 value, I will end show, and for what I am going to do is, I didn't enable the edit. Maybe I didn't enable the edit. Yeah, there is a text option. So the induced voltage E1, the induced voltage E1 is given by E1 is equal to number of turns on the primary. Okay. So let us assume number of turns on the primary side are N1. Okay. So what I am going to do is I will write N1. Okay. And this N1, I can, is there any option? I can move it here. So let us assume number of turns on the primary side are N1. Okay. And similarly, number of turns on the secondary side are N2. N2. Number of turns on the secondary side are N2. Secondary side means what? Secondary side means secondary winding side. This is my secondary winding. This is my primary winding. So supply voltage V1 is given to the primary winding. So when current I1 flows through the primary winding, what is happening? Since the primary winding is wounded around the ferromagnetic material, which can be easily magnetized, so what will happen? Flux is induced when when current flows through a coil, and within the coil, if there is a core, then definitely core gets magnetized and flux is induced. This flux will travel from this limb to the other limb. So where on the other limb another winding is there. So number of turns in the other limb, number of windings on the other limb, number of turns on the other limb are N2. Number of turns on the first limb were N1. Let us assume. The number of turns in the primary winding is N1. Number of turns in the secondary winding is N2. Then the induced voltage E1 is given by E1 is equal to, it will depend on the number of turns N1 into d5. Okay, d5. 5 means flux. Okay, phi means flux, d phi by dt. So I am unable to use my cursor to write it on the screen clearly. That's why I'm using the other way. So here I am unable to find the phi. So this here somewhere phi will be there. So let us consider this as our phi, d phi by dt. d phi by dt. So the induced voltage on the primary side is what? E1 is equal to N1 into d phi by dt. This N1 equal to subscript. Okay. So N1 is the subscript. So what is E2? E2 will be equal to, I'll better insert an equation. It will be more clear to understand. Okay. This is our diagram. Something has happened here. Okay, once again, I will insert the equation so that it will be Yeah. So I will write here E2. E2 is equal to N2. I will write capital N2 into D phi. So this was my phi. D phi by dt. Okay. So this is my equation for E2. This is my equation. Both equations are same. I have written. It may seem they are different, but both are same. Okay. So I didn't use the equation mode to write even equation. That's it. So this is the induced voltage. So, sorry, where is it? And this is the induced voltage in the primary winding, E1 equal to N1 into d phi by dt. And the induced voltage in the secondary winding, E2 is equal to N2 into d phi by dt. It's very simple. Okay. So what is d phi by dt? It is the rate of change of flux linking. Okay. So rate of change of flux means how flux is varying with respect to time. Okay. That is d phi by dt. So what is E1? E1 is the primary, is the induced voltage in the primary winding, which is proportional to what? N1. Okay, number of turns. And similarly, E2 is the secondary induced voltage in the secondary winding, which will be proportional to the number of turns in the secondary winding. Okay, the induced voltage will be proportional to their respective turns. Okay, so if E1 is induced in N1, so E1 will be proportional to N1. E2 is induced in this secondary winding, so E2 will be proportional to N2. Okay, that is it. Now, here I am showing you one type of this port. So ports depend. There are types of transformers actually. So, there are types. So before going to the types, let us discuss the working principle. So let us discuss the working principle of the transformer. Working principle of the transformer. So the transformer works on the principle of the mutual inductance. Okay. Between two windings linked by a common magnetic flux. So here two windings are there. We can see primary winding. Okay, you can see a primary winding and a secondary winding. Okay, so both are linked by a common flux. That is our main flux or useful flux, isn't it? Okay, and this transformer has two windings which are wounded around the limbs of this core. And whenever supply is given to the primary winding, what is happening? Flux is induced in the core. That flux will travel through the core towards the secondary winding. Okay, when this flux cuts the windings, what is happening? EMF is induced in the secondary. Of course, EMF is also induced in the primary winding. Okay, and whatever flux that is traveling from primary to the secondary, that is our useful flux. Whatever flux is leaking in the air, that is our leakage flux. And the induced EMF across the primary is E1 equal to N1 into d phi by dt, and the induced voltage across the secondary is E2 into E2 is equal to N2 into d phi by dt. Okay, so to be to speak in more detail, so what happens here is actually when supply is given to the primary winding, flux phi is induced, flux will travel in the core and it will cut the primary windings. Okay, I'm sorry, it will cut the secondary windings. When the flux cuts the secondary winding, if there is a load connected, what will happen? I2 current will flow. I will show the other image so that I can explain it to you. Okay, now. So here you can see. So phi is traveling from primary to secondary. Now, when current I2 flows through the primary, I'm sorry. I think when current, I'm unable to find my cursor and I'm speaking something. Yeah. when current I2 flows through the secondary winding, what will happen is, when current I2 flows through the secondary winding, what will happen is, because of I2 current, another flux phi 2 will be induced in the core, and because of that current I2 current, flux phi 2 will flow into the core in the opposite direction to the actual flux. Okay, so to understand it more clearly, so let us assume the current due to current I1, the flux that is flowing in the core is phi 1. Now, due to current I2 also flux is induced, and the direction of that flux will be exactly opposite to phi 1 flux. Okay, and let us assume that flux is phi 2. Okay, phi 2 flux is induced in the core because of I2, and phi 1 flux is induced in the core because of I1. Okay, due to current I1, so phi 1 flux is induced in the core, which is proportional to I1, and phi 2 flux is induced in the core, which is proportional to, sorry, my cursor is not listening to me. Because of that, I don't know what I'm doing. Okay. So, phi 2 flux is induced in the core, which is proportional to I2. Okay. So, phi 2 flux is induced which is proportional to I2. Phi 1 is produced, which is proportional to I1. Now, these two fluxes, they are opposite to each other. Therefore, whichever is the majority will be usually the supply current flux, means definitely phi 1 will be, sorry, phi 1 will be greater than, phi 1 will be definitely greater than phi 2. Okay, phi 1 will be greater than phi 2. So these fluxes will cancel each other, equivalent fluxes will cancel, and resultant flux that is left over in the core is phi. Okay, so and that resultant flux phi, it will travel from source towards the load. This is what happens in the transformer. Okay, this is what happens in the transformer. So we have seen the working principle of transformer. Now let us see the types of transformer. So the transformer can have two types of cores. Just now what we have seen here in this diagram, this is core type transformer. Okay, so depending on how the core is constructed, transformer can be core type or shell type. Transformer can be core type or shell type transformer. Depending on whether the transformer is stepping up the voltage or stepping down the voltage, whether it is increasing the voltage level or decreasing the voltage level, transformer can be step up transformer or step down transformer. Till now, is there any issue? If there is any issue, please inform. So, depending on the type, the core construction, okay, how core is constructed, transformer can be core type or shell type transformer. Okay, so there are further you can even classify the transformers based on the type of service. Based on the type of service, transformer can be power transformer, distribution transformer, instrument transformer, current transformer, potential transformer, or auto transformer. And based on the supply that is given, it can be a single phase transformer or three phase transformer. Now today what I'm about to discuss here, of course I have already started the discussion, is a single phase transformer. Okay, so let us discuss this core type and shell type transformer. So if it is a core type transformer, this is how the core of the transformer will be. Okay, if it is core type transformer, this is how the core of the transformer will be. So in this core type transformer, the magnetic circuit will be consisting of two vertical legs or limbs with two horizontal sections. They are called yokes. Okay, two vertical, where is my cursor? So there will be yeah. So there will be two vertical limbs, as I've already told you, and two yokes, upper yoke and lower yoke. Okay. So and the windings are placed in such a way that we don't want any leakage of flux, isn't it? Even though flux is induced in the core, what is happening? Flux may, I said that flux will leak in the, while there will be leakage of flux while traveling from this limb to another limb. Okay. So in order to avoid the leakage of flux, what is done is half of each winding is placed in each leg of the core. Okay, half of each winding will be placed in each leg of the core. For low voltage winding, okay, so you can see here LV, you can see if you carefully observe, this is LV. Low voltage winding is placed first, and after that, high voltage winding is wounded in order to avoid the leakage on this limb. Similarly, low voltage winding is wounded around the, I'm sorry, low voltage winding is wounded, means low voltage winding is placed nearer to the limb. Low voltage winding is placed nearer to the limb, and high voltage winding is placed after that. Okay. So in order to avoid the leakage of flux. Okay. So low voltage, high voltage, low voltage, high voltage. Similarly, and around this limb, low voltage and high voltage. Okay. So these two windings are arranged in concentric coils. Such type of coils you will call it as concentric winding or cylindrical winding. So the winding that is provided around the core type transformer, you can call them as concentric winding or cylindrical winding. Now let us see the shell type transformer. Okay, so this is our shell type. I'm sorry, I didn't show you. This is our shell type transformer. Let me see whether I have shell type somewhere. Yeah, this is our core type. No, this is shell type. So I will show you. You can see this is our shell type transformer. So you can see it has three limbs. Okay. So you can see here there are three limbs. Limb 1, limb 2, and limb 3. This is our core type. So it has two limbs. Okay, you can see primary winding and secondary winding of your core type transformer. And okay, if you carefully observe these windings, they are like concentric coils. Okay, or cylindrical winding, we will call them as cylindrical winding. So besides to this, you can see shell type transformer. So the shell type transformer, okay, both the primary winding and secondary winding, if you carefully observe here in this image, both the primary winding and the secondary winding, they are wounded at the same limb. Both the primary winding and secondary winding are wounded at the same limb, that is at the central limb. There are three limbs. In the central limb, both primary and secondary windings are wounded. Okay. So here, low reluctance path is completed by the outer limbs. The outer limbs means this limb and this limb, they are the outer limbs. The low reluctance path will be provided by these outer limbs. Each winding is subdivided here into sections, low voltage and high voltage subsections. Okay, each winding, primary winding, secondary winding, they are subdivided into low voltage section and high voltage subsections. They are alternatively placed in the form of sandwich. Okay, these windings are alternatively placed in the form of sandwich. That's why this winding is called sandwich or disc winding. This winding is also the shell type the winding of this say a shell type transformer. You can call it as sandwich or disc winding. So you can see that somewhere here. Let me see. I will show you that image. I am having that. Yeah, this is our sandwich or disc winding. They on the central limb windings are wounded like a sandwich. Okay, that's why it is named as sandwich or disc winding. So you can see primary winding and secondary winding here. So you can see here on the primary winding, this is core type. In the core type, you can see 110 volts by 120 volts. And when you step up, it has become 220 volts by 240 volts. So this is a step up voltage. Okay, so now let us see how it is manufactured. This is step down voltage transformer. You can see 220 volts by 240. It is stepped down to 110 by 120. Okay, this is step down transformer. Okay, so this is our step up transformer. Okay, and this is our step down transformer. So to manufacture this core type and shell type, so I have some images of core type and shell type. I will show you. So these sort of transformers you can see. Okay, so this is some grid. So you might have seen on the poles transformers. So this is one image of the transformer. Here also transformer. Okay, so this is our core type transformer. You can see concentric cylindrical winding, primary and secondary winding, how they are there. And this is our shell type. You can see this here one limb is the under limb. At the central limb, winding is provided to the transformer. Okay, this is it. Now let us see the construction of the transformer. How transformers are constructed. So So transformer core, you can see we have discussed two types of cores. One is core type, another one is shell type. Okay, so this is core type, this is shell type. Okay, so let us see how transformer is constructed. So transformer consists of what? Magnetic circuit. What is magnetic circuit? Magnetic circuit is formed by what? Magnetic circuit is formed by the flux. Okay, the flux which it starts from its journey from the primary, uh, from the limb of the primary winding to and return back. It travels through the limb of the secondary winding and return back to the primary winding limb. So it forms a complete closed magnetic circuit and electric circuit. Current is flowing through the primary winding, of course, and because of the mutual inductance, current flows through the secondary winding also. That is our electric circuit. Okay, so the main parts of the transformer are what? Main parts, let us see. Main parts of the transformer are the primary winding, secondary winding, and the core. So you can call this core as steel core. Okay, so the steel core, it is usually made up of silicon steel in order to provide continuous magnetic path. Okay, so usually the core of the transformer is laminated. So laminated means they will take thin sheets. Okay, they will take thin sheets and they will provide insulation in between each and every sheet, and they will assemble one above another. They will stagger them one above another, okay, to form the core. You can see this is a thin sheet for core type transformer, and you can see some n number of sheets. Okay, so in between each and every sheet, proper insulation is provided to avoid the leakage of, okay, to avoid the leakage. Similarly, you can see this is shell type transformer. These are the thin sheets. They are staggered one above another to form the shell type core. Okay, and usually to form these cores, so if it is core type transformer, the laminating sheets, they will take two L type laminating sheets, they will join together to form the core type lamination, or they can take U-shaped lamination and I-shaped lamination, and they will join together to form the core type lamination. Or for shell type, they may take E type and I type join together to form the shell type. They may take two E's and join together to form the shell type. Okay, so this is shell type lamination. This is core type lamination. So the sheets are staggered together to form the core type or shell type. Okay. Okay, so these thin sheets, you know what I have told you, these thin sheets, they usually their thickness will be around 0.25 mm to 0.5 mm. Okay, and these laminations are they are fixed together by some studs or rivets or bolts. Okay, they are staggered one above another. They are fixed together by some bolts. Okay, and they are provided with proper electrical insulation. So this is it, the construction and the working principle. So let us discuss few more parts of the transformer. Let us discuss few more parts of the transformer. Transformer tank. So you can see here, this is a transformer. This is our main tank. Whatever is mentioned, you can see in this image. I will just increase this image. Okay. So this whatever main tank it is mentioned here. Let me check whether I am in the class or not. So are you able to follow or not? Are you able to follow the class? Okay then, transformer tank. So transformer tank, it will have, it is to have a longer life, better service for the transformer. Uh, all the different parts are fixed to the transformer tank, and actually the transformer purpose, tank purpose is to um, the purpose of the transformer tank is to provide proper insulation to the transformer core and the windings. Okay, so in the transformer oil is filled. You can see another image here. So this is primary winding, secondary winding, and this is inside portion of the tank. So it is filled with oil flow. You can, I don't know whether it is visible or not. So it is filled with oil. Another image is there. See here. So this yellow portion, what you can see, this whole yellow portion, it is the oil, transformer oil. So it is filled with proper oil to provide proper insulation to the transformer windings. To provide proper insulation to each and every part of the transformer tank is used. Okay, so above the transformer tank, there is, you can see a circular portion that is the known as conservator. Okay, so conservator will be cylindrical in shape, and it is, you can call it a cylindrical tank placed above the top on the roof of the transformer tank, main tank. So it acts as a reservoir of transformer insulating oil. So it oil will be poured in this conservator. Now, whenever the oil level in the within the transformer, you can see that transformer is fully filled with oil. So if the oil level decreases, if the oil level decreases within the tank, then immediately the oil from the conservator will move towards this transformer tank and it will fill the transformer tank. So oil level may decrease because of faults, internal or external faults. Okay. Uh, okay, or because of aging. Okay, after certain period, the oil will be ages. Aging means its performance will reduce. Okay, it ages means its performance will reduce. So as the oil ages, means it becomes old. Okay, as we humans become old and we won't be able to perform all the tasks properly as we are able to do now. Similarly, if the oil ages or if any faults occur within the transformer, then because of the faults, if the oil level reduces, that oil level is maintained by the conservator. Okay, that is the purpose of the conservator of your transformer. Okay, so even under normal operating condition, if suppose the transformer is fully loaded, okay, so means if load is connected to the transformer, it is fully loaded, then the temperature of the transformer will raise to high value. Okay, the temperature may raise. and an increase in the volume of the air inside the transformer may takes place because of the raise in the temperature. Volume air level may inside the transformer may increase volume of the air. Okay, so because of that, oil level may increase sometimes. Okay, sometimes it may happen. Oil level may increase or decrease. It depends. If oil level increases, if there is no space for the oil to move, then it may damage the pressure inside the transformer tank may increase. Okay, so what should happen if oil level increases? That oil may move towards the conservator. Okay, if suppose oil level increases because of temperature increase, okay, in the transformer, whenever transformer is fully loaded, so that during that condition, the oil has to be disposed to somewhere. Of course, we are not disposing it, but it has to be. It acts as an backup, like a backup layer. So it just preserves the oil there. Conservator. If oil level increases, that oil will shift to the conservator. If oil level decreases, from the conservator, oil will move towards the will move within the tank, and it will always maintain the oil level within the transformer tank. Now let us see what is meant by a breather. This is a breather. Okay, so breather acts as the heart of the transformer. Okay, breather is the heart of the transformer. So whenever temperature within the transformer increases, okay, what will happen? Temperature increases means the oil gets heated up. Transformer oil gets heated up. So if the oil of the transformer gets heated up, what will happen? The oil level may expand. Okay. So if the oil cools, then oil level may contract. Okay. So whenever oil level increases and oil expands, so what will happen is this breather breathes air in, and what will happen? It will try to cool the oil. Okay, but it won't allow any moisture to enter. Okay, it won't allow the moisture to enter into the transformer oil, but it will allow the air to be absorbed into the tank, so that it will help the heat in the oil to get away. Okay, in order to cool the oil, okay, it breathes the air without allowing the moisture to enter into the air. Okay, so the purpose of the breather is to absorb the air, not the moisture. Okay, so that's why it is called as the that's why it helps to helps the transformer to breathe, we can say. So it helps the transformer to breathe. So if suppose the breather, okay, if the breather is absorbing, if suppose oil level has increased within the transformer, um, and if the breather absorbs the air from the atmosphere, and it just lets the oil to cool down, okay, the oil may carry the moisture. So I'm sorry, the air may carry the moisture. Just now I told you, it won't allow the moisture to enter. It allows only the air to enter the transformer. Okay, so now to eliminate this air, eliminate the moisture from the air, what is used is silica gel. Silica gel is nothing but some crystalline rocks. Okay, crystal rock like things. Okay, they will be blue in color. Okay, so they will be blue in color. So you can see here, this is the breather. The crystal rocks will be blue in color. They are known as silica gel. Okay, these crystal rocks, they absorb the moisture from the air. They will allow only air to enter into the main tank. Okay, and they will help the oil, the quality of the oil to be maintained. Okay, so whenever they are absorbing the moisture from the air and allowing only air to enter into the tank, this blue color silica gel will convert into pink color. So you can see two images here. In this image, all the silica gel, they are crystalline alloys, we can say. They are the alloy rocks. So they are blue in color here. But in this image, some of the silica gel crystalline rocks are converted into pink. They convert into pink because of the absorption of the moisture, okay, from the air. Okay, so now let us go back to the image. So you can see here, there is a vent which is known as expulsion vent. Let me see in any, yeah, you can see explosion vent, it is mentioned here. Okay, explosion vent. So this explosion vent is a thin aluminum pipe placed at the both ends of the transformer. Okay, it is placed at both ends of the transformer to prevent the transformer from damage. Okay, so when the temperature increases in the transformer drastically, if temperature increases means oil level will increase and excess pressure will be created within the transformer. So there are chances for the transformer to explode. Okay, so in order to release that pressure, this explosion vents will release that pressure. Okay, so the purpose of the explosion vents is to release the pressure that is developed within the transformer. So whenever oil level increases. Okay, now let us see what is meant by these radiators. These are the radiators. You can see these are the radiators. Main purpose of this radiator is to cool the transformer. Okay, so to cool the transformer. So indirectly to cool what here, what is getting heated up? Transformer oil is getting heated up. So to cool the transformer oil, these radiators will help. So the radiator is a detachable device. Okay, so the upper portion and lower portion of the radiator is connected to the transformer tank. Okay, so let me show you some other image. Yeah, you can see this in this image. You can see this is the radiator. Okay, so this is the radiator. Upper portion and lower portion of this radiator is connected to the transformer tank. Okay, by a valve. Okay, by a valve, with the help of valve, they are connected to the transformer tank. So when the transformer cleaning and maintenance are done, then the valve will prevent the draining of the oil when the radiator is detached from the transformer. So whenever oil gets heated up, what will happen is through the upper valve, the oil will enter the radiator. Okay, through the upper valve, the oil will enter the radiator. Okay, and it will just cool within the radiator. You can see even cooling fans are provided in the radiator. And after cooling, it will return back through the lower valve into the transformer tank. Okay, that's the purpose of our radiator. Now let us see the bushings. You can see here bushings. I mentioned bushing. These are the bushings. So the bushings in the transformer are the insulating devices that allows electrical conductors to pass electrical energy safely through it. Okay, so it will allow the electrical conductors to pass the current safely through it. So this is it. This is the electrical bushing. So you can see electrical conductor. This is the conductor, copper conductor. You can see it's mentioned here, conductor. This is the copper conductors. So bushings in the transformer are the insulating material that allow electric conductor to pass electrical energy without any um, electrical hazard. Okay. So this insulation that is provided here, these are the insulating material. So these insulators are made up of solid porcelain. Okay. This is it. I think it is more than sufficient. Okay, we have seen the working principle and the construction. I think it is enough. So let us go to the induction, three-phase induction motor. Three-phase induction motor. If you have any doubts regarding what I have discussed, you just mention in the chat box. I'll try my best to clear your doubts. If you are unable to follow, just inform me. So let us see what is three-phase induction motor. Okay. Let us see what is three-phase induction motor. So we know electric motor. We know electric motor. So electric motor, we know it is an electrical machine that converts electrical energy into mechanical. Sorry, yeah, electrical energy into mechanical energy. So depending on the type of power supply that we give, okay, so the motors can be classified as DC motors or AC motors depending on the supply. So if we give DC supply to the motor, it is our DC motor. If we give AC supply, that is our AC motor. If we are able to give both AC and DC supply to the motor, then that is known as universal motor. So depending on the supply that you give, you can categorize the motors into DC motors, AC motors, and universal motors. Okay, so this is it. This is our induction motor image. Of course, even DC motors also look alike. Okay, so our subject is what? Three-phase induction motor. So since our subject is three-phase induction motor, so this three-phase induction motor is an AC motor which works on the principle of electromagnetic induction. Okay, so it works on the principle of electromagnetic induction. So you call the AC motors which work on the principle of electromagnetic induction as induction motors. Okay, so the AC motors to which supply is AC, to which AC supply is given. Okay, the AC motors to which AC supply is given. The principle with which they work is known as electromagnetic. Sorry, they work on the principle of electromagnetic induction. So they are known as induction motors. Okay, so why we are using induction motors? Because of the following advantages. Because they are simple in construction, they are easy to start, and we can easily control the speed of these motors, and their efficiency is good. Okay, because of good efficiency, we will use induction motor. Okay, are you able to follow the class? Is there any disturbance? If any disturbance is there, just inform. Okay then. So here you can see this is our three-phase induction motor. So if you see the construction of three-phase induction motor will have stator and a rotor. Okay, stator is the static part of your three-phase induction motor. Rotor is the rotating part. In your DC machine, you will have poles and armature. Okay, poles are the static part, armature is the rotating part. Similarly, in your induction motor, here core is the static part. Okay, core means here stator. We will call this is our static part. This is the, you can see here, this is our stator and this is our rotor. And the stator will be consisting of three-phase winding that can be connected to the power supply. And rotor is free to rotate. This is a rotor that is free to rotate. It has short circuited winding. Okay, it will be having short circuited winding, the rotor. So let us see the stator. So this is the stator of three-phase induction motor. So it is the stationary part. It is the stationary part of the motor. Okay, stator is the stationary part of the motor. So it is made up of steel frame which encloses a hollow cylindrical core. Okay, so which encloses a hollow cylindrical core. The core of this three-phase induction motor is made up of silicon steel laminations. Okay, this core is made up of silicon steel laminations. Lamination means thin sheets are taken. Okay, thin sheets are this it. You can see this is also stator core. So here along with the stator windings, you can see the core. So thin laminations, as I have shown you for your for the transformer just now. So similar to that, here thin laminations are taken. They are staggered one over the another to form this core. Okay, they are placed one over another to form this core. So this core is formed by thin laminations. Okay. So the main purpose of using thin laminations is, so I'm checking whether do I have any other image. I don't have any other image. Okay. The main purpose of using thin laminations is to reduce the hysteresis losses and eddy current losses. I think you know what is meant by hysteresis and eddy current losses. Okay. So inside the core there will be slots. Okay, so you can I don't know whether it is visible in this image. There will be slots. Okay, at the inner periphery of this stator there will be slots in which stator windings are provided. You can see windings here. This yellow color copper color stator windings. Inside the inner periphery windings are provided. Okay, so these windings are insulated, which are provided in this slot. They are properly insulated and they are connected in such a way that they either form a star connection or delta connection. They either form a star connection. So this is known as, the windings are connected in such a way that they form a star connection. Star connection means you can see this is a three-phase induction motor. So we know, if we say single phase, it will have a phase and a neutral. So if we say three phase, it will have three phases. Okay, R, Y, B phases. Okay, this is R, this is Y, this is B. It will have three phases. So this is one winding, another winding, three windings. They are interconnected to a common point that is known as neutral. So this is star connection of the stator windings. This is the star connection. These windings, here you can see these windings. These windings, they may be connected in star form or they may be connected in delta form. This is delta connection. R, Y, neutral point when they are connected in delta. They may be connected in star form. This is star connection. They may be connected in delta form. Okay. So what is the stator? Stator is what? It is a steel frame which is hollow which has a hollow cylindrical core, isn't it? If you look at it carefully, it is cylindrical, almost cylindrical in shape, and it is hollow inside. Okay, and there will be slots inside in which windings are provided. So you can see here windings are provided. Okay, and these windings, they may be either star connected or delta connected. Okay, and the supply that is given to these windings is three-phase supply. Okay, R, Y, B, you can see three-phase supply is given to these stator windings. Okay. Now let us see the rotor of the three-phase induction motor. Rotor of three-phase induction motor. So the rotor is usually mounted on the shaft. So you can see a rod here. You can see a rod here. It is usually mounted on the shaft. So it is a hollow laminated core having slot on its outer periphery. So on the outer periphery, outside, there will be slots. Slots means just holes in which conductors can be placed. Okay. So the windings are placed in these slots. You can see here this brown color, they are the windings. So they are placed in these holes. You can see small holes here. Okay. So this is one type of rotor. This is another type of rotor. This is slip ring rotor. This rotor is slip ring. This is squirrel cage rotor. This is known as squirrel cage rotor. So rotor of three-phase induction motor, they can be two types: slip ring rotor or squirrel cage rotor. So here, if it is a squirrel cage rotor, this is squirrel cage rotor. Squirrel cage rotor will be consisting of laminated cylindrical core. Okay, laminated cylindrical core having parallel slots on its outer periphery. This is the outer periphery which has parallel slot. So one copper or aluminum bar is placed in each slot. Okay, in each slot, one copper or aluminum bar is placed. I think I have another image, squirrel cage. This is squirrel cage. So you can see these are the rotor core in which copper bars are placed. Okay. So all these copper bars, you can see they are joined at the end to the end ring. So copper end ring, you can see this is the end ring. So these rotor bars are joined at the end ring. Okay. And these end rings are permanently short circuited. Okay. These end rings are permanently short circuited. So you can see another image. So this is squirrel cage rotor. You can see rotor bars. They are short circuited by the end rings. Okay. So see, if you look at this, it looks like a case, isn't it? It looks like a case. That's why it is named as squirrel case. Okay. So this rotor is not connected electrically to the supply. No supply is given to the rotor. So to these two rotors, whether it is slip ring or squirrel cage, to both the rotors supply is not given. So current will flow in these wires or windings purely due to induction, like transformers. In our, we have seen in the transformer, when current flows to the primary winding, what will happen? Current starts to flow in the secondary winding if secondary winding is connected to the load. Similarly, when current flows to the stator windings, in the rotor, current will start to flow. Okay, in the rotor windings, current will start to flow purely due to induction. Okay, purely due to induction. So you can see rotor bars and end rings here. So purely due to induction, current will start to flow in the rotor of your three-phase induction motor. So most of the three-phase induction motors are squirrel cage type rotors. They will be having squirrel cage type rotor because they are simple and robust in construction. Okay. So one of the disadvantage of squirrel cage rotor is that it has low starting torque. Okay. So the squirrel cage rotor will have low starting torque. So starting torque will be very, very low. So what is meant by torque? What is meant by torque? Torque means what? Angular displacement around the axis is nothing but the torque. Okay. So because of low starting torque, the rotor bars, it is because of rotor bars are permanently short circuited. Okay. So since the rotor bars are permanently short circuited, it will have low starting torque. So we can't add any external resistance to this circuit to have large starting torque. So if you want to have large starting torque, then it's better to go for slip ring type rotor, which is also known as wound rotor, WOUND, wound rotor. So it consists of laminated cylindrical core. Okay, let me see. Do I have any image? This is it. So this is it. It has a laminated cylindrical core with the three-phase winding. Okay. So the rotor winding is uniformly distributed in the slots and usually star connected. So these windings of this rotor, so you can see here, the windings of the rotor are usually star connected. This it will have slip rings, okay, to collect the current or to give out the current. Okay, so the open end of the rotor windings are brought out and joined to the three-phase insulated slip rings. So these are three-phase insulated slip rings mounted on the shaft. This rod, inside rod, that is known as shaft. So three brushes are connected here. It is not shown here in this diagram, but brushes will be connected to to uh, connected to be connected. They are connected to three brushes are connected to three-phase star connected rheostat. Okay, so that I will show you. Another image is there that I will show you in that image. So you can see the brushes. So here these are the slip rings. So this colored brown color portion is the brushes. So then external resistor rheostat is connected here. Okay, so the purpose of external rheostat is to increase the to have high starting torque. Okay, so in order to have high starting torque at the starting of the motor, these resistors will be connected to the circuit. Okay, so as soon as motor picks up the speed, gradually these resistors will be disconnected. That is. So this is the construction of squirrel cage type, and there is one more type, slip ring type rotor. So let us see the working principle of the induction motor. So how it operates, and so let us see in detail. Okay. So if you see this image, I will just expand it. So you can see here, this is our rotor. You can see three poles in the stator. Okay. So this is our stator. So in order to understand the concept, you can see it is a simple diagram has been given here. So to the stator, what is given? Supply is given. What supply is given? Three-phase supply is given. I'll just expand the. I'll just expand this image. I want a bigger image. So this is it. So when three-phase supply is given to the stator winding, it will produce a magnetic field. Okay. So when current flows to the stator winding, so what will happen is it will produce a magnetic field. That field is known as rotating magnetic field. In your transformer, what is happening? When current flows through the primary winding, magnetic field is produced, flux is produced. Similarly, here also, when current flows to the stator windings, flux is produced. That flux is known as rotating magnetic field. Okay, so once the rotating magnetic field is produced by the stator windings, okay, so an electromagnetic induction happens, okay, between the stator and rotor. Okay, so what will happen because of when flux is produced, what will happen? This flux will interact with the rotor windings. So you can see blue color dots here. These blue color dots are the rotor cross-sectional view of the rotor windings. These brown color wires are the stator windings. These are the stator windings. These blue color dots are the rotor windings. So what will happen? When flux is induced, when current flows through the brown wires, you can see here stator windings. When current flows to these stator windings, these are the stator windings. So when current flows to the stator windings, flux is induced. The flux will travel from north pole to south pole, and by traveling, it will interact um, with the rotor windings. So there will be an electromagnetic induction, means they will have mutual induction, okay, or there will be magnetic coupling between the both stator and the rotor. Okay, something is wrong. Okay, so since the rotor windings are short circuited here, similar to your transformer, So what will happen? Current will start to flow through the rotor windings. In your transformer, current will start to flow through the secondary winding. Similarly, here also current will start to flow through the rotor windings. Now, when current is flowing through the rotor winding, similar to your transformer, as I said that if phi 1 flux flows through the core because of I1 current in the primary winding of your transformer, phi 2 current will be induced in the core due to the current I2 current in the secondary winding. Similarly, here also, because of the current in this primary stator windings, rotating magnetic field is induced. Okay. And when the magnetic field interacts with the rotor windings, current starts to flow through the rotor windings. Why? Because rotor windings are short circuited. So now, because of the current flow in the rotor windings, rotor also will induce its own magnetic flux. So already rotating magnetic field is there in the stator windings, and rotor is also inducing the magnetic flux. Now there will be an interaction between rotor magnetic field and the stator magnetic field. Okay, there will be interaction between rotor magnetic field and stator magnetic field, and a torque is produced. Okay, so a torque is produced. Because of that torque, what will happen? Rotor will start to rotate. Because of that torque, rotor will start to rotate. So here, transformer, we can say induction motor works on the principle of the transformer. Here, stator windings are acting as primary winding, rotor windings are acting as secondary winding. Okay. So here, the supply that is given, wait. So the supply that is given is three-phase supply to the stator windings. You can see R, Y, and B. These are the three phases. Okay. So I have been telling you that rotating magnetic field is produced in the stator windings rotating. So what is meant by rotating magnetic field? Let us see. Okay, so let us see what is meant by rotating magnetic field. So this means the rotating magnetic field means the magnetic field will be rotating. Okay, the magnetic field that is produced in the because of the in the stator core, because of the current flow in the stator windings, it will be rotating in nature. So we know for the voltage to induce, okay, for the voltage to induce, either magnetic field should move or the conductor should move. Okay, so here magnetic field that is produced in the stator will be rotative in nature. So why it will be rotative in nature? The rotating magnetic field is produced depending on the how the stator windings are arranged. Okay, depending on how the stator windings are arranged. Okay, so the rotating magnetic field will depend on how the stator windings are arranged. It also depends on the frequency. Okay, and alternating property. It also depends on the alternating property of the three-phase AC supply that is given to the stator windings. Okay, so we know in our AC supply the current, the magnitude and the polarity of the AC supply will be continuously changing with respect to time. Okay, and magnitude always reaches the zero value and the peak value. Okay, in your AC supply, the magnitude will always reach the peak value as well as zero value, isn't it? So these are the three phases. Now, if you observe, I have told you that there are three phases R, Y, B. So if you see, I will take a pen. If you see, here R is maximum. At this instant of time, R is maximum. At the same instant of time, what about blue line and yellow line? R is red. Okay, three phases. R, Y, B. R, Y, B means red, yellow, and blue. Red phase, yellow phase, and blue phase. Three phases are there. Red phase, yellow phase, and blue phase. Three phases are there. So when red phase is peak, means it is having its peak value. What about the yellow phase and blue phase? Are they maximum? They are not reaching their maximum value. Okay, they are not maximum. They are some low values. Similarly, when yellow is maximum, here you can see at this instant of time, yellow is maximum. What about at this instant, blue and red? They are not maximum. Okay, they are not maximum. Similarly, when blue phase is maximum, okay, so the magnitude of blue phase when it is maximum, both yellow and red are not maximum. Means we can see that first R phase reaches its peak value, then Y phase reaches its R phase reaches its, wait, I will erase all things. Okay, we can see R reaches the peak value first, next Y reaches peak value, next B reaches the peak value, one after another, isn't it? These three phases are reaching their peak values one after another. Okay, so this property will help to produce the rotating magnetic field in the induction motor. Okay, okay. So let us consider, just to understand the concept, let us consider stator has coil A, coil B, and coil C. Stator has coil A, coil B, and coil C. Okay, so but there will be many coils. To understand the concept, this diagram has been used here. Okay, now coil A is connected to what? You just carefully observe. Coil A is connected to R, isn't it? Coil A is connected to R. Coil Y, coil B is connected to Y, and coil C is connected to B. You just observe the image carefully. A, this is A. Okay, this is A that is connected to R, and this is B, coil B that is connected to Y. Coil C is connected to B, and all these three phases are connected to neutral. All the three phases, they are connected to the neutral. Okay, this is how they are connected here in the given circuit. Okay. So now if three-phase AC supply is applied to the stator windings, okay, to the stator windings, if three-phase AC supply is given, this is three-phase AC supply is given. So according to the nature of the supply, okay, first coil A will be energized. Why? First R is becoming peak value. R is getting the higher peak value. Therefore, coil A gets energized. Okay, next coil B gets energized. Next, because after R, Y is becoming the peak value, it is getting its peak value, and later when coil C is energized, coil C will be energized. Why? Because at last B gets its peak value. Okay, so first coil A gets energized, next coil B gets energized, next coil C gets energized, and this will happen repeatedly depending on the frequency of the supply. This will repeat. Okay. So all these three coils are not energized at a time. Okay. So one after another they are energizing. Okay. That's why because of this effect. Okay. Because of this effect, what will happen? The magnetic field that is produced here, it will be rotating in nature. Okay. And as the magnetic field rotates, the rotor of the induction motor will also rotate with respect to the rotating magnetic field. Okay. The rotor of the induction motor will also rotate with respect to the magnetic field. Okay. So induction motor has many applications. So it is used in pumps, submersibles, pressure machines, lathe machines, grinding machines, conveyors, floor machines, compressors, and in many low mechanical power applications. Okay. These are the applications of induction motor. So let us discuss the alternator also. I wanted to conclude this even if many of you have not joined the class, but it's okay. I want to complete the syllabus irrespective of how many of you have joined the class. Okay, so if you people don't have interest, what can I do for that? My job is to be done. I want to do my job. Okay, it has to be done. That's it. So I can't help it if most of you won't join. It's your wish. Okay. My job is to complete my work. That's it. So alternator. So alternator is an electrical machine. Okay, this is the construction of alternator. So, do I have any other image? So alternator is an electrical machine that converts mechanical energy into electrical energy. So what is generator? Generator converts mechanical energy into electrical energy. So similarly, alternator converts mechanical energy into electrical energy. Of course, generator or DC generator we have already discussed. This is an AC generator. Okay, this is alternator is nothing but an AC generator, which is also known as synchronous generator. Okay, it is also known as synchronous generator. It generates specific voltage at specified frequency. Okay, it generates the specific voltage at specified frequency. So if you see the construction of the alternator, I'll just expand this. Okay, so it has a rotating armature and a stationary magnetic field. Okay, it has a rotating armature and magnetic field will be stationary in the alternator. Okay, so armature windings are placed in the stator. Field windings are placed in the rotor. Okay. So this generator, it is also known as alternator or AC generator or synchronous generator. So it will have stationary magnetic field and rotating armature windings. Okay. So alternator is made up of stationary, okay, whatever I'm sorry. So field windings are in the armature and armature windings are in the stator. So it will have a stator and rotor. Okay. And the armature windings will be placed in the stator and in the rotor field windings will be placed. So rotors can be two types, salient pole type or cylindrical pole type. So you can see this is one type of rotor, this is another type of rotor. So okay. So here what is done is to the rotor windings. This is a rotor. To the rotor, supply is given. DC supply is given to the rotor windings. You can see the windings here. So you can see in the slots cross-sectional view of the windings here. So to the rotor windings, supply AC supply is given. Sorry, DC supply is given, not AC supply to energize the windings to produce the field, magnetic field. Okay, field winding. So they are the field winding. To the field winding, we already know some small supply voltage is given. Okay. Now, when this rotor rotates, what will happen is magnetic field will be generated. Okay, this varying magnetic field generates. Okay, so when this field winding rotates, when current flows to it and it rotates, what will happen is it will cut the field. The magnetic flux is rotating here. It will cut the conductors of your stator winding. Okay, and EMF is induced in the stator winding, and that induced EMF will be given to the load. Okay, so this varying field generates EMF in the armature windings, which are placed in the stator, slots. So these slots are at the inner periphery. So you can see blue, yellow, and red. You can see blue, yellow, and red. So they are the armature windings in the stator. Okay, they are the armature windings in the stator. So now if you see the rotor, so it can be salient pole type or cylindrical pole type. So what is rotor? It is the rotating part of the alternator, okay, which carries the field winding here. Okay. So let us see salient pole type rotor. Salient pole type rotor. So in this type of rotor, it has large number of protruding or projecting poles. You can see these are projected outwards, isn't it? North pole, south pole. There are 4 poles here. They are projected outwards. Projected outwards. So these poles are projected outwards. So a salient pole rotor will have projected poles mounted at the core of the laminated sheet. Means this core is also made up of laminated sheet, steel or cast iron. Okay. So the term we are calling it as salient. Why? Because the poles are projecting outwards. Okay, that's why it is named as salient. Okay. So the field coils, you can see they are wounded here across the poles. Okay, and they are connected in series. Now let us see the cylindrical type. This is cylindrical type. So it can have 2 poles or 4 poles. You can see 4 poles are there, north, south, north and south. They are the 4 poles. Okay, this is also made up of laminated steel sheets. They are staggered one above the another to form a cylindrical structure. You can see, you are unable to see the cylindrical structure. I am showing you the cross-sectional view. Okay, so this type of rotor has slots. You can see here slots. These are the slots in which field windings are placed. You can see field winding. I'll take the laser. So you can see the field winding. In these slots, field windings are placed. You can see the cross-sectional view of the field windings. These field windings, similar to your previous case, they are connected in series. Okay. So since the poles are not protruding outwards, they are not projected outwards, this cylindrical pole type rotor, it is known as non-salient type. Okay, or round rotor. You can call it as a round rotor or non-salient. Okay. So usually this rotor will have very small diameter, which larger length. Okay, so because of its cylindrical structure, it will have mechanical strength and it is robust in construction and it can uniformly distribute the magnetic field. And it will have lower winding losses. Okay, means leakage of current will be low. So it is suitable for high speed and noiseless operation. Okay, so the salient, non-salient or cylindrical pole type rotors of alternators, they are designed for high speed alternators such as thermal power station AC generators. Okay, in thermal power stations they are used. Now let us see the stator. Let us see the stator. So this is our stator. Stator is what? It is the stationary part of electrical machine. Okay, and it is used for holding the armature windings. Okay, armature windings are placed in the stator and EMF is induced in these windings. So here I will take the laser. Okay, so see in these slots you can see blue, yellow and red. They are the conductors. They are the armature windings. EMF is induced. Voltage is induced in these conductors. So here this core is also made up of laminated sheets. They are staggered one above another to reduce the hysteresis and eddy current losses. Okay, so the rotor rotates inside this stator, but while rotating, the rotor will never touch the stator. Okay, it will never touch the stator. So stator means static part, means it will not have any rotating part, no moving parts. Okay, so outer current, output current is directly drawn from the bushes that are connected. Brushes are not shown in this diagram. Brushes will be there. Here you can see three-phase output terminals, R, Y, B terminals. You can see. Okay, so from the brushes directly supply is connected. means this will give the energy to the load that is connected to it. Okay, supply, another supply is not connected, it itself generates the supply. Okay, it itself generates the voltage. That voltage is through the with the help of brushes given to the load. Okay, so it is simpler in design and construction. Okay, so it is usually, it can even generate high voltages. Okay, now if you see the outer portion, dark blue portion, that is known as yoke. Dark blue portion is known as yoke. So yoke is the outermost part of alternator that provides the mechanical support and protects the inner parts from environment damages or pollution and all. Okay, next, let me see what else do I have. Okay, slip rings and brushes. Slip rings and brushes. So I have this image, so I thought I will show you this. So these are the slip rings. Okay, slip rings, and you can see black box here, square box here also. They are the brushes. Okay, so slip ring is the component that transfers electrical power between stationary and rotating parts of the machine. Okay, it transfers its electrical power between the stationary and rotating parts of the machine. So it is used to transfer DC power to the rotating field windings from a DC battery using brushes. Okay, so the brushes will be sliding on the slip rings, and they will collect the current from the slip rings and they will give it to the purpose of brushes is that. Okay. Now let us see the working of the alternator. This is working of the alternator. So it works on the principle of Faraday's law of electromagnetic induction. So we already know whenever a conductor moves in the magnetic field, what will happen? Voltage is induced and current flows through the conductor. Or when a conductor moves in the magnetic field, then also voltage is induced. Either conductor has to move or the magnetic field has to move. Okay. So here you can see same diagram you might have seen for the DC machine. So here you can see north pole, south pole, and here conductor. This is our conductor coil, single coil. It is rotated in the magnetic field. Hence voltage is induced. That voltage is induced collected by the slip rings. Okay, and it is given to the load through the brushes. Okay, so in which direction the EMF is induced, that can be determined by Fleming's right hand rule. So in this Fleming's right hand rule, if you stretch your thumb, forefinger, and your middle finger. Okay, so if thumb represents the direction of force and forefinger represents the direction of the magnetic field, then the middle finger will represent the direction of the EMF induced. Okay, the direction in which the voltage is induced in the alternator, it can be determined by this. Okay. Okay. So in the stator, as I have already told you, there will be three phases: phase 1, phase 2, phase 3. Usually the angular displacement between the phases will be around 120-degree displacement. Okay. So the phase angle displacement between will be 120-degree. Okay. So you know one complete cycle will have 360. So if we divide equally into three parts, okay, one complete cycle will have 360. If we equally divide into three parts, each angle should be equal to 120 degrees. So if you have three phases and if you want equal angular displacement between those three phases, then that should be equal to 120 degrees. So here these three phases, phase 1, phase 2, and phase 3. they will have equal angular displacement of 120 degrees. So this is one. Okay. Now, whatever EMF or the frequency of the induced EMF, okay, it will be proportional to the rotor speed and number of poles. So F will be equal to N into P by 120. The frequency of the induced EMF is induced, isn't it? Voltage is induced in this alternator. The frequency of that induced EMF will be always equal to N into P by 120. Okay. So the applications of the alternators is they are used to generate the power in the power stations. They can be used in automotives and locomotives. They can be used in aircrafts and radio frequency transmission systems. They can be used in industrial industries. Okay, they can produce standby and emergency power. Okay, yeah, they can also be used in renewable energy system. They can be used in marine and navy boat applications. So if okay, I hope you have understood. It's my keyboard.